Hi, class. So we have another snow day this Thursday, so we're going to have another video lecture. So we're jumping back into chapter 5, but the last unit, which is chapter 5E, which is on correlation and causality. So I think we've often heard that nice phrase, correlation does not mean causality, but we're going to look at it a little closer. So first we're going to define what a correlation is. So a correlation exists between two variables which I'm going to abbreviate as VARs, two variables, when higher values of one variable consistently goes with higher values of another variable, or when higher values go with lower ones. One variable go with lower values of another variable. Nice long definition for us for a correlation. So when it says higher values consistently go with higher values, it means if you have like a high value of like 1,000 people, maybe we'll get a high value of like a population of a city, something like that, where on the X and Y axes, we can like give high with high, low with low, or we can do high with low values and low values with high values, something like this. So can imagine these two slopes. And that's going to the slopes of these kind of imaginary lines are going to tell us if we have positive or negative correlation. That should be our next point. Okay, so first we're going to talk about some examples of correlation, and then we will be able to talk about positive and negative a little bit better. Okay. Examples of correlation, which I'm going to abbreviate as core a lot. So there is a correlation between the variables height and weight for people. Okay. So what this means is taller people tend to weigh more than shorter people. And this is a tends to. There's always going to be some like counter examples, but it's a tending. So if we kind of imagine having axes, maybe we have weight and we have height. I'm just going to abbreviate. Usually the shorter you are, you weigh a little less. So maybe we'd have something kind of like this for a scatter plot of them. And of course, there could be someone who's really short and weighs a lot, or someone who is really tall and doesn't weigh very much. So you can get some counter examples. But typically, if you're going to be 6 feet tall, you're going to have just some mass to you because you're so tall. All right. And then another example, there is a correlation between the variables, demand for apples. So the whole demand for apples is one variable. And my S is sad. There we go. And the price of apples. So i.e., what that means, the way we can kind of see that, the demand decreases as prices increase. It's kind of, we can think of that even specifically with like eggs right now. Eggs are getting a lot more expensive, so the demand is kind of going to go down just because it's so expensive, people might not be buying as many eggs. So then for the picture on this one, we're going to have price, and we're going to have demand, which I'm going to write as a D. And so when the price is really low, the demand's going to be pretty high. But as the price gets higher, people aren't going to be buying less and less. So we're going to have something like this, maybe. And I'm just kind of doing some random dots to give an idea. So, and then lastly, what we're going to look at is one last example. So there is a correlation between practice time, oops, and skill among piano players. Okay. So, i.e., the more you practice, the better you play. Oops. Okay. So again, if we think of practice versus play, the more we practice, the better we play. So if we've never practiced, we might not be that good, but as we practice more and more, people tend to get better. And of course, there's going to be some savants that like never practice and just were naturally good. But for the most part, most people, the more you practice, the better you get. Okay, so that's kind of getting the idea behind causation and of correlation. And so the way that I've been drawing all of these pictures, kind of to give us a graph, these are called scatter plots. All right, so a scatter plot is a graph in which each point represents the values of two variables. Okay, so for an example, let me get some more room. So maybe on one side we have temperature in like degrees Celsius, and on the other side we're going to have sales in dollars. Okay, and this is going to be of ice cream specifically. So we might have a couple of points. So let's think maybe really cold temperatures, we're not selling that much ice cream. Maybe we're selling some more here. We just get a couple of data points. Like this. They're kind of spread out. Again, if it was on Alex, they'd have like a better kind of labeling system. I'm doing the best I can on this little whiteboard. So we can kind of see the nice correlation here. We like to imagine there's kind of a nice dotted line right here through the middle, and everything kind of hugs that dotted line. So if we have this nice dotted line that a lot of our data points are hugging, that's going to be a nice strong correlation. If we don't really have a clear line for our data points to follow, that's not going to be very strong correlation. All right, so going off of that, we can have no correlation as one of our options. Okay. So that means there is no apparent relationship. So a graph of that might look like this. It just could be a lot of scattered points. There's no clear line anywhere. I'm just really just drawing a bunch of random points. So like there's no good line. Like if I draw a line here, that's not really good. So if there's no clear line, you're going to have no correlation. Okay. So then we could have positive correlation. Again, I'm going to start abbreviating again as core. So that's both variables tend to increase. So as one goes up, the other one goes up, and the to increase or decrease. Together. So I like to think of that if we have the nice scatter plot. I'm going to draw the line first. We're going to have a positive slope. So if the slope of the line is going up, then we're going to have positive correlation versus, so let me underline positive because that's one of our definitions. All right, and then we're going to have negative correlation, which is just going to be the exact same thing, but with a negative slope. All right, so one variable increases while the other decreases. I guess I probably should have wrote negative all the first time before I start abbreviating. Okay. So same idea with a nice picture. Same thing, I'm going to draw a slope in first. We have a negative slope. And we'd have some data points going down with a negative slope. So positive slope, negative slope, that's the difference. Okay. And then we can talk about the strength of the correlation. So okay, you know what? I'm just going to draw a picture to represent it. Describing it in words is kind of hard because just seeing it is going to be easier. I'm going to use positive for both of these. Okay. So for stronger and weaker, that's our kind of two options. Whoops. Okay. So for stronger, we're going to kind of imagine this line of best fit. as being a really strong magnet. Everything is really close to this line here. Everything's really, it's a really strong magnet. Most of the data points really follow this trend line. They don't deviate too much from it. Or something's a little bit weaker, maybe I allow some more variation in my data points. They're not quite as tight together right along the line. There's just a little bit more breadth to it, but they still do follow the nice line here. We can kind of see that there's a clear line, even if it's not, sorry, my slashes are getting a little weird. All right, so we can see the difference here between nice tight points that all stay pretty close to the line, and they still tend in the same direction, but the points are a little bit more scattered versus what we saw earlier with the no correlation. I'm going to go back up, where there's no good line. It's just a bunch of random stuff. Like if I drew another line in here, maybe something in a different color, there's a lot of data points around that one too. Versus down here, I have a little bit of wiggle room kind of throughout here, but the line like slope would be about the same. Like, yeah, maybe I could do another one a little bit down here, but not really to get the actual like closeness of all of these points over here. There's just and this is about equidistance from all the points. It's a little bit more spread, but it still clearly follows the line. Again, this is where I typically would ask for questions, but there's no one here. Okay. So I'm going to show one other slide. I'm going to like show you a slide example real fast, so I don't have to draw everything on the board. Okay. So looking at the slide, we have this nice strong positive, strong negative, weak positive. So it's a lot more spread there. You can kind of see, but it's still generally going up. We have moderate negative. So like there's a little bit more spread, but it's not quite as spread as this weakness. Then we have none. There's just a bunch of dots everywhere. And this is a pretty weak negative, but you can still see it kind of still tends down. But what we really like are the two strong ones and even the moderate. Okay. So with that now, we're going to, since we've seen all of these, we're going to jump back to a handout, which is back here. There we go. Okay. I'll go to the handout here. Let's go back to the top. Okay. Let me just double check it's at the same. Yeah, it's on the correct one. Perfect. Just had to double check. Okay. So if we have the given scatter plot below, we want to state whether it shows positive, negative, or no correlation, and if it's positive or negative, how strong is it? So here we have the average income in thousands of dollars, and then we also have the life expectancy in years. And we kind of see here that if we imagine there's kind of a line going right along here, they do fit in pretty nicely. Right here is a lot more varied, but kind of as we go, it tends up. And it's, well, again, I can't write on this one. It's not the whiteboard, so we just have to talk about it. Oh, maybe I can. Oh, here we go. Okay. So, perfect. Make it a little thicker. There we go. You can kind of imagine that there, ooh, that might be too thick. There we go. Kind of imagine that there's a line kind of like that. Imagine it's perfectly straight. And we can see it has a slight positive slope to it. It's not super positive. It's not a very big slope, but there is a slope. And I would say that this one is for, and then it's, I would say it's pretty strong. It's a little bad right around this part here. It's not the best, but I would say strongly positive. So the conclusion would be the higher your income, the longer you live. And this is again on average. It's a tend, it's a like statistical likelihood, not a guarantee. That makes sense. If you have a lot of money, you can go to a lot of doctors. All right, so for this next one here, for part 2, the graph shown below shows a relationship between the age of drivers and the number of accidents per 100 drivers in the year 2009. So we have age as our x-axis and accidents per 100 drivers as our y-axis. And again, you can kind of imagine that there's a nice little line here, got a little bumpy in the middle. So this one has a negative slope. And I think this one has more data points that are more spread. I know this one had a little bit of a bad points, but then everything else was really tight. This one's a little bit more widespread, so I would probably say weakly or moderate and negative. So this is as you get older, like into your 25s, the less accidents you get. So that's kind of, I'm not going to write it, I'm just going to say it. Okay. And then lastly, we have this scatter plot here. And so notice that like if I was to draw a line here, there's some really far out points all over everything. And if I was to undo all of those and draw a line like here, totally different line, or even a line, I don't know, here. They're all kind of equally bad. So I would say this one has no correlation. That means there's no correlation between the number of hours you sleep at night and your shoe size. Which makes sense. That doesn't seem like there would be anything related to those two things. Okay. So let's jump back into the slides and writing. Oh, wait, I forgot. The slides are on here. Let's go back to this. There we go. Okay. Lots of jumping around, I know. Okay. So this is where we start talking about correlation does not cause or mean causation, and about how we can like help determine that. So, oops, shouldn't be in red anymore. The correlation should be kind of a new topic. May be a coincidence. All right. So that's kind of the one option. The second option is there's a common underlying cause. Okay. Okay. So that means like, let's say we are looking at accents of a class, like how many like Southern accents are there, and I'm only looking at classrooms that are like in the Deep South. I would expect there to be a high correlation of Southern accents when I'm picking schools in the Deep South. That would be the underlying cause is like where they're all were raised. That's kind of like an example. There's going to be some better examples. I'm coming up with one off the top of my head. And so for 3, oops, one of the correlated variables may actually cause, or be a cause, sorry, of the other. It may just be one cause. Be one of several. Okay. And so again, the big note correlation does not equal causality. My eyes are looking very sad. There we go. So to get 3, it's very hard to prove that. We can guess and estimate, but we cannot, it's very, very hard to prove this causality part. So we're not going to focus too much on how they get that, but about when we can and like when we can maybe detect. Okay, so with this, in statistics, a spurious correlation, oops, Jesus, this doesn't work. Okay, a spurious correlation or a spurious crazy word refers to a connection between 2 variables. The connection that appears causal this is not going to work. So, but is not. So this is the like definition of correlation does not mean causality. So sometimes it's chance, sometimes it's unknown factors, but this is like the spurious correlation. It's the example of when it's not a causality. Okay, so like an example, let me go back and show y'all. Would be here, a spurious correlation example. So the per capita consumption of mozzarella cheese correlates with civil engineering doctorates awarded. So we can kind of see the graph. The black is the engineering doctorates. The red is the mozzarella cheese consumption. And we can see that these are pretty strongly correlated together. They are, which is kind of crazy, but it's really like nothing would be causing this. I mean, unless every single time a civil engineer was awarded their doctorate, they went and bought mozzarella cheese. But even that would be such a crazy thing for every one of them to do. So it's very much like they're not causing each other. So some more examples, more of these fun little memes. So there's just a lot, and I'm gonna let you guys kind of read through these as they go. I'm gonna just keep, because this is a lot of words now that are less effective for me to actually write. So here's some guidelines for establishing causality. If you suspect that a particular variable, the suspected cause, is causing some effect, there's some guidelines to check. So first, you look for situations in which the effect is correlated with the suspected cause, even while other factors vary. All right. Among groups that differ only in the presence or absence of the suspected cause, check that the effect is similarly present or absent. And then look for evidence that larger amounts of the suspected cause produce larger amounts of the effect. If the effect might be produced by other potential causes besides the suspected cause, make sure that the effect still remains after accounting for these other potential causes. If possible, test the suspected cause with an experiment. If the experiment cannot be performed with humans for ethical reasons, consider doing experiments with animals, cell cultures, or computer models. So this would be like crash test dummies instead of real people and testing for cars. And then try to determine the physical mechanism by which the suspected cause produces the effect. So this is very much like, I feel like almost in the language of like a drug study. A lot of medicine will go through things like this. Going through testing of different drugs is a long and arduous process. So they have to have very strict guidelines for that, and they're kind of modeled off. These are a little bit more general, but this like kind of idea holds for any type of study of causality. But I feel like the most common ones typically have to do with like medicines. Okay, so here's a case study for airbags in children. So by the mid-1900s, passenger side airbags had become commonplace in cars. Statistical studies show that the airbags save many lives in moderate to high-speed collisions. But we also had a disturbing pattern appear. In some cases, young children, especially infants and toddlers in car seats, were killed by airbags in low-speed collisions. So it's like we found a correlation between airbags and small children's being killed. So they wanted to do an experiment to see, is it the airbags that are causing this or is it something else? So obviously you don't want to risk actual children in their studies, but so at first many safety advocates found it difficult to believe that airbags could be the cause of the deaths, but because of the correlation kept getting stronger and stronger, they had to look at it. So, because it's indicated that being closer to the airbag increased the risk of death, a child sits in the top of a built-in seat, thereby putting them closer to the airbag. So kind of, I know that there's a lot of words here. I'm kind of just summarizing some of these. So then we continue to go down. So to seal the case, safety experts undertook experiments using dummies. So again, you don't want to risk real children in the experiment, so they're going to use dummies. And so they recommended that they needed children in the back seat away from the airbags because while like the safety of adults living through high, moderate, and high speed crashes was so much more, they didn't want to risk children, so they found a nice compromise of children now sit in the back. And that really lowered the amount of child death due to airbags. So that's an example here. And then another one here. Let's look at confidence in causality. Okay, so possible cause. We have discovered a correlation, but cannot yet determine whether the correlation implies causality. That's why we use possible. So in a legal system, possible cause, such as thinking that a particular suspect may have caused a particular crime, is often the reason for starting an investigation. Probable cause is we have good reason to suspect that the correlation involves cause. So perhaps one of the guidelines for establishing causality are satisfied. In the legal system, probable cause is the general standard for getting a judge to grant a warrant for a search or wiretap. Then we have cause beyond a reasonable doubt. We have found a physical model that is so successful in explaining how one thing causes another that it seems unreasonable to doubt its causality. In the legal system, cause beyond reasonable doubt is the usual standard for conviction. It generally demands that the prosecution show how and why, essentially the physical model, the suspect committed the crime. Note that beyond reasonable doubt does not mean beyond all doubt, so it's just reasonable. Okay, so that's again how causality kind of plays a part in the real world. And that is going to be the end of our causality and correlation section. We are going to change subjects and chapters and sections when we get back, hopefully in person next week. Again, if you have any questions on any of these slides or lectures during the snow day, feel free to email me or talk to me when we're back in person. We will still have the quiz and the homework due this Sunday. So I'm trying to record this Thursday lecture early because I was a little late on getting you guys the Tuesday one just because I had to figure out how to record a lecture during the snow day. So hope all is well with y'all, and I will see y'all next week. Although now it's taking me a sec to sign off.